In this video, I'm going to discuss few more problems on the topic of potential energy and stability of equilibrium. So this question is a solved problem in the R.C. Hibbeler text. It reads that the uniform link shown in the figure has a mass of 10 kg. Okay, one can see here there is a link AB in the form of a rod or a bar. Its mass is given as 10 kg and its length is equal to 0.6 meters. If the spring is unstretched when theta is equal to 0 degrees, determine the angle theta for equilibrium and investigate the stability at the equilibrium position. So first of all, what is given here? That when theta is equal to 0 degree, the spring is undeformed. Okay, and what will be the position of the link when theta is equal to 0? One can see that this link is making an angle of theta with the vertical. Therefore, when theta is equal to 0 degree, the link AB will be vertical. This link AB will be vertical. So what will be the position of the link when theta is equal to 0? Let's see. This roller B would be somewhere here, and this roller A will be somewhere here. And the position of the link will be, the link AB will be completely vertical. Okay. So this is the state of the system when theta is equal to 0 degrees. And one can clearly see from the figure that this length of the spring, that is this length shown here, is the undeformed length of the spring, because when theta is equal to 0, the spring length is the undeformed length. That is, the spring is unstretched when theta is equal to 0 degrees. So this will be the unstretched length of the spring L naught. Okay. And when theta is going to increase from 0 degree to some value of theta, one can see that the spring is getting stretched. So in this position shown here, one can see that the extension in the spring is X. The spring is getting displaced by this much amount. Okay. So one can also see that the displacement, or the rather the extension in the spring, that will be depending upon the vertical displacement of the roller. So initially the roller was here, the spring was undeformed, and the distance traveled by the roller in the vertical direction will be actually equal to the displacement or the extension of the spring. Okay, that will be equal to the extension of the spring. So one can see here in this position, when this link is making an angle of theta with this vertical, the spring is in the stretched state, or we can say that it is in the extended state. Therefore, in the free body diagram, the restoring force will point in this direction. Okay, that is, the spring force will be in this direction, and the weight of this bar is vertically downwards. Okay, if this is the center of gravity, the weight of this bar can be shown here. In addition to these two forces, in the free body diagram, we can show the reaction at B, and we can also show the normal reaction at A. Okay, normal reaction at A and normal reaction at B. But one can see that the roller B is constrained to move in this direction. Either it can go towards right or it can go towards left. Therefore, in any case, this reaction and the displacement of the roller B will be in the will make an angle of 90 degree. Therefore, the virtual work due to this reaction will be 0. Similarly, this roller A can move upwards or it can move downwards, and the normal reaction is always perpendicular to the displacement of the roller. Therefore, again, the work done by this normal reaction will be 0. Okay. Therefore, we can say that the normal reactions are inactive forces. Whereas in this case, the active forces are the spring force and the weight. So both of these forces are also conservative forces. Okay, so when all the active forces in the system are conservative forces, we can use the potential energy criteria for equilibrium. Therefore, the potential function can be written as the summation of gravitational potential function and the elastic potential function. Okay, this term will be there will be some value of the potential energy function because the spring is in the deformed state. Okay, currently it is in the extended state. Therefore, it will possess the elastic potential energy and it will also have the gravitational potential energy. Okay, so let's find out these two terms. Okay, so first of all we have to establish the datum. So this yellow color plane passing through these two rollers can be treated as the datum. This is the roller A and the roller B when the system is in the undeformed state, or when the theta is equal to 0. Okay, when the theta is equal to 0 and this length of the spring will be the undeformed length of the spring, that is, it's equal to L naught. Okay, so this is the position of the system when theta is equal to 0 and the spring is in the undeformed state. But as theta is going to increase, the spring is getting stretched by the same amount by which this roller is displacing in the vertical downward direction. And this is the position of the roller B at any angle theta. Okay, so one can see that this displacement of the roller A, okay, initially it was here and its final position is here. Therefore, during this displacement x, okay, if x is the vertical displacement of the roller, then it will be also equal to the stretch in the spring. Okay, and one can easily find out the stretch in the spring. Okay, it will be the difference of, see, this distance. Okay, this distance is equal to L because L is the length of this link AB, and this length is equal to, from this right angular triangle one can clearly see that this is the length L. Okay, this is the length L of the roller, so this length will be equal to L cos theta, and the stretch in the spring will be equal to this L, this distance minus this distance. Therefore, it will be equal to L minus L cos theta, and it can be written as L into 1 minus cos theta. So we have found out the stretch in the spring. Now we can write the elastic potential energy function. Therefore, the elastic potential function will be 1 by 2 kx square, that should be equal to 1 by 2 k into L into 1 minus cos theta. This will be square. So the elastic potential function will be equal to 1 by 2 kl square 1 minus cos theta square. So this is the potential energy function, elastic potential function. Okay, now let's write the gravitational potential function. See, the center of gravity of this bar is above the datum by this much amount of distance. Let's take this distance to be y. Then the gravitational potential function can be written as the weight of the roller, sorry, the weight of this bar multiplied by the vertical height of the center of gravity from the datum. And this center of gravity is lying above the datum, therefore the potential function will be treated as positive. And one can clearly see from this figure, this angle will again be equal to theta, and this BG distance is equal to L by 2. Therefore, this y is equal to L by 2 cos theta. From the right angular triangle, it's clear that this distance is equal to L by 2 cos theta. Therefore, the potential energy function, okay, gravitational potential function can be written as, this weight can be written as the product of mass and acceleration due to gravity, and this vertical height of the center of gravity from the datum is equal to L by 2 cos theta. So hence we have written both the gravitational potential function and the elastic potential function. Now we can add them to get the total potential function, that is, the total potential function can be written as the summation of gravitational potential function and the elastic potential function. This Vg is equal to mg L by 2 cos theta plus this elastic potential function is equal to 1 by 2 k L square 1 minus cos theta whole square. Okay, also we know that for equilibrium dv by d theta, that is the first derivative of the potential function with respect to any independent coordinate. Now see here, this theta is enough to determine every position or every configuration of the system. Therefore, it is a single degree freedom system. This should be zero. Okay. So once we have established the potential function in terms of the coordinate, okay, independent coordinate, after that it's only the calculus portion. Okay. So the mechanics portion ends here, and now only the few steps of mathematics are required. So if we calculate the first derivative of this function, we can write dv by d theta, it is equal to mgl by 2. The derivative of cos theta is equal to minus sine theta, therefore plus 1 by 2 kl square. The derivative of this 1 minus cos theta whole square, it will be equal to twice 1 minus cos theta, and the internal differentiation of this 1 minus cos theta, that will be equal to 0 minus sine theta, that will be plus sine theta. And this derivative should be 0. It will be equal to minus mg L by 2 sine theta plus 1 by 2 kl square. Okay, so this 2 and 2 will cancel out, so we can skip this. It will be equal to kl square it will be 1 minus cos theta multiplied by sine theta. So this term should be 0. We can take L sine theta common here, and in the brackets we will have minus mg by 2 plus kl 1 minus cos theta. So this has to be 0. Now we will get two values of theta. Okay, for the equilibrium condition, we will get two values of theta. The first is sine theta should be 0, which implies that theta is equal to 0 degree. Okay, so this is one value, and another value can be found out by this term in the brackets. This should also be 0 for this whole term to be 0. Therefore, we can write minus mg by 2 plus kl 1 minus cos theta, that is this term in the brackets. This should be 0. Or we can write 1 minus cos theta. This can be equal to mg by 2kl. Okay, or we can write that cos theta is equal to 1 minus mg by 2kl. We can substitute the values. The mass of the bar is given as 10 kgs multiplied by 9.81. The spring constant was given as, let's look at it. It's given as 200 Newton per meter, and the length is equal to 0.6 meters. Okay, so from here we can calculate the cos inverse of this term, and we will get that theta is equal to 53.88 degrees. Okay, so these are the two values of the theta for which the system will be in equilibrium. Now we have to investigate the stability of the equilibrium. And for the stability of equilibrium, I have to calculate the second derivative of the potential function. Okay, so let me write the first derivative again. It was equal to dv by d theta. This dv by d theta was equal to minus wl by 2 sine theta plus kl square 1 minus cos theta sine theta. Okay, so this is the equation which was here. Okay, minus WL by 2 sine theta plus KL square 1 minus cos theta sine theta. Okay, mg I have written as the weight. So if we calculate the second derivative of this equation, it will be equal to minus WL by 2, the derivative of sine theta is equal to cos theta, plus KL square. Now this can be solved by the UV rule of the differentiation. We can keep 1 minus cos theta here, and the derivative of sine theta will be cos theta. And in the next step, we can keep sine theta as it is and compute the derivative of 1 minus cos theta, that is 0 minus minus sine theta, that will be plus sine theta. So this is the second derivative. So if we can evaluate this, it will be equal to cos theta minus cos square theta and this will be equal to plus sine square theta. Now in this question, we have to check the second derivative, okay, at two values of theta, that is at theta is equal to 0 degree and theta is equal to 53.8 degrees. So first of all, seeing what is the second derivative of the potential function at theta is equal to 0 degree. So if we substitute theta is equal to 0 degree, so first of all, we can see that sine theta will be 0, cos 0 is equal to 1, minus cos square theta is also 1. So 1 minus 1 will be 0, and this term is also 0. So this whole term will be 0, and cos 0 is equal to 1. Therefore, this second derivative, when theta is equal to 0 degrees, this will be equal to WL by 2. So actually, it will be equal to minus mgl by 2. And if we substitute the values, it will be equal to minus 10 into 9.81 into 0.6 divided by 2. So this term comes out to be minus 29.43. So from here, we can conclude that, therefore, theta is equal to 0 degree. Now we got a negative value, okay? At theta is equal to 0 degree, the system is in unstable equilibrium. Okay. Similarly, we have to evaluate the second derivative of the potential function at theta is equal to 53.8 degrees. Okay. And this comes out to be, once you put the value of theta is equal to 53.8 degrees in this equation, okay, solve it yourself, and this will come out to be plus 46.9. Okay. So this value comes out to be positive, and this indicates that at theta is equal to 53.8 degrees, the system is in stable equilibrium. Okay, so the previous value corresponded to the unstable equilibrium, and this value is corresponding to the stable equilibrium. Let's look at one more problem. It is an unsolved problem in the RC Hibbler. It reads that the spring on of the scale has an unstretched length of A. Okay, so one can see here, this is the length A, and this is also equal to the unstretched length of the spring. Therefore, If I extend this line, this is the unstretched length of the spring. And one can clearly see from the figure that currently the spring is in the stretched state, because it will be equal to this extension x1 plus this extension x2. Okay, so if this is the unstretched length of the spring, that is A is the unstretched length of the spring, one can see there in this position of the system, the spring is in the stretched state. And this stretch or extension in the spring is equal to x1 plus x2. Okay, so this is the total extension in the spring. Okay, determine the angle theta for equilibrium when a weight W is supported on the platform. You can see there is a box whose weight is equal to W. It's on the top of this link. Okay, neglect the weight of the members. We have to treat all these links to be massless. Only the weight has to be taken into the account of this box. Okay, what would be the value W required to keep this scale in the neutral equilibrium? So we have to see what is the value of W. Okay, what should be the value of W such that the system is in neutral equilibrium when theta is equal to 0 degrees. Okay, so this is the question. Okay, therefore we have to find the value of W here. Once again, we can see that in the free body diagram there will be the reactions at the two hinges, but they won't be active forces because they won't create any displacements, hence they won't be responsible for any kind of virtual work. Here again, the active forces are the spring force, okay, because the spring can get extended or compressed. Okay, currently it is in the extended state. Okay, therefore if I want to show the free body diagram of this system, the spring force will be pointing here, and here the spring force will be pointing in this direction. Okay, because the spring is in the extension, therefore the restoring force will be such that they will again compress it to the undeformed state. So one can see that the active forces, they are weight and the spring force. And both these forces are conservative forces. Hence, we can use the potential energy criteria for equilibrium. We can write that potential function will be equal to the summation of the gravitational potential function and the elastic potential function. So to write the gravitational potential function, if this is the center of gravity, this is the center of gravity of the weight. Okay, what is the distance of the center of gravity from the datum? Let's suppose that this horizontal plane passing through these hinges is the datum. Okay, so what is the height of the center of gravity from the datum? That will be the, we have to find the height of the center of gravity from the datum. Okay, so one can see that the height of the center of gravity, it will be equal to the summation of the distance from this point to this point plus some distance of this center of gravity from the here. Okay, so if I take the length of this or the height of this box to be 2b, then the distance of center of gravity from this horizontal link will be b. Okay, and one can see that from the right angular triangle, this height will be equal to, okay, this height is equal to L cos theta. Similarly, this height will also be equal to, this height will also be equal to L cos theta. So the height of from this point to this point, it will be equal to 2L cos theta. Therefore, I can write that height is equal to 2L cos theta, but it is only the height of the, okay, from this point to this point, but we have to add the height from the center of gravity. Okay, we have to see what is the height of the center of gravity from the datum. So this b will be added here. Okay, plus b. So this is the total height of the center of gravity of this block from the datum. It's equal to what? Summation of this L plus cos theta and this L plus cos theta, and also the height of this center of gravity from this horizontal link. Okay, if I take this length to be 2b, therefore the height of the center of gravity from this horizontal link will be b. Therefore the summation of all these three heights will give us the total height of the CG of this block from the datum. Okay, so once we have found the height, we will be in the position to write the gravitational potential function. Therefore this gravitational potential function will be equal to the weight, that's W, and the height. Okay, the height of the center of gravity from the datum, it's equal to 2L cos theta plus B. Okay, and this gravitational potential function will be positive because the CG is located above the datum. Therefore it is capable of doing the positive work, hence it is potential function is positive. Okay, so this is the potential function, gravitational potential function. Now if we look at the elastic potential function, it is given by half of kx square, where x is the total extension in the spring. Now one can clearly see that x will be equal to summation of x1 and x2. Now this x1 is equal to, from the right angle triangle, one can clearly see that from this right angle triangle, this x1 is equal to L sine theta. Similarly, from this right angle triangle, one can see that this x2, it is also equal to L sine theta. Therefore, the total extension in the spring is equal to 2L sine theta. And we can write the elastic potential function as 1 by 2 k x is equal to the total extension in the spring, that is equal to 2L sine theta whole square. Okay, so once we have written the gravitational potential function and the elastic potential function, we can make their summation to get the total potential function. So this V will be equal to Vg plus Ve. The gravitational potential function is equal to, it's equal to W into 2L cos theta plus B this is the gravitational potential function, and the elastic potential function is equal to plus 1 by 2 kx square, and x was equal to 2L sine theta. So this V will be equal to 2WL. Okay, let's keep it here, or we can solve it as well. 2WL cos theta plus WB plus 1 by 2 k into 4L square sine square theta. So this can be written as 2WL cos theta plus WB plus 2KL square, okay, 2KL square sine square theta. Okay, now using the equilibrium criteria, for equilibrium, the first derivative of this potential function with respect to theta, this should be 0. Therefore, if we compute dv by d theta, it will be equal to minus 2WL cos theta. The differentiation of this is 0 because weight is constant, and this height b is also constant because the height of the block is constant. Therefore, the derivative of this WB will be 0 plus 2KL square, the derivative of sine square theta, it will be equal to twice sine theta, and the internal differentiation of sine theta, that will be equal to cos theta. So this term has to be 0. So from here we get that we can take cos theta to be common. Okay, we can take cos theta to be common. If cos theta is common, in the brackets we can have 2WL plus 4kl square sine theta. This should be 0. So apology for this slight correction here. And this is 2wl cos theta, and its derivative will be 2 minus 2wl sine theta. Correct this here. And once this 2wl sine theta is common, so kindly make a correction here. The derivative of this 2wl cos theta is minus 2wl sine theta. So from here, actually, sine theta will be common. So we'll have sine theta as common. And in the brackets, we will have minus 2wl plus 4kl square. And since sine theta is common, in the brackets, we will have cos theta. So here, actually, we will have cos theta. So now we'll get two values of theta for equilibrium. So first value will be when theta sine theta is equal to 0 degrees, which implies that theta is equal to 0. Okay, it's not degree here. Sine theta is 0, and this theta will be 0 degrees. And another value will be given by this term in the bracket should also be 0. That is minus 2wl plus 4k l square cos theta. This has to be 0 for equilibrium. And from here, we can see this 2 and 2 can cancel. This L and L will cancel. So we will get 2kl cos theta is equal to W. And from here, we can get that theta is equal to cos inverse W by 2kl. So what we have to do actually in this question is that it's given that when theta is equal to 0, what value of W should be, okay, what value W is required to keep the scale in the neutral equilibrium when theta is equal to 0 degree, okay? So it says that when theta is equal to 0 degree, the system is to be taken in neutral equilibrium, okay? Then what should be the value of W such that at theta is equal to 0 degree, the system is in neutral equilibrium? So we also know the condition for neutral equilibrium. The second derivative of the potential function with respect to theta is 0. So if we compute the second derivative of this potential function, so the potential function is equal to minus 2wl. I can write this potential function again. It is equal to minus 2wl sine theta. So first of all, I will write dv by d theta again. It's equal to minus 2wl sine theta, okay? Minus 2wl sine theta plus 2kl square in brackets we have twice sine theta cos theta, and this can be written as minus 2wl sine theta plus 2kl square, and in place of twice sine theta cos theta we can write sine 2 theta. Now we can calculate the second derivative, okay? Differentiating this again, we'll get the second derivative of the potential function with respect to theta, and that will be equal to minus 2wl cos theta plus 2kl square. The derivative of sine 2 theta will be cos 2 theta, and the internal differentiation of 2 theta will be 2. Therefore, twice cos 2 theta. So for neutral equilibrium, this has to be 0. Okay, 0 for neutral equilibrium. And we have to check the condition of what should be the weight when the system is in neutral equilibrium when theta is equal to 0 degree. So we'll put theta is equal to 0 degree. Okay, see the question again. It's clearly mentioned that what value W would be required to keep the scale in neutral equilibrium when theta is equal to 0 degree, okay? So this is the neutral equilibrium, and if we put theta is equal to 0 degree, then what should be the value of this weight? Therefore, it will be 2WL cos 0 will be 1 plus twice KL square. It will be twice cos 2 theta, that is cos 0 again will be equal to 1. So this has to be 0. So from here we get that 2WL should be equal to twice KL square multiplied by 2, that will be equal to 4 KL square. So from here we will get the value of W to be, it will be equal to 2KL. So this is the required value of weight for system to be in neutral equilibrium at theta is equal to 0 degrees. Okay, fine.